Greetings, everyone. So my name is Shankar. I'm from SRI, and this is the first of a session of tutorials that we'll have. They're very informal, mainly to get to know how to use proof assistance. So today I'll spend the next 50 minutes or so talking about PVS, and then Andreas will talk about ACTA. So very quickly, PVS stands for Prototype Verification System. Actually, the story behind it is that we started calling it the People's Verification System, but once you start dealing with the US government saying people's anything is going to be a red flag, so we changed the name to Prototype Verification System. And at some point it made sense because we meant it to be a research prototype, but we still mean it to be a research prototype. It's something that we experiment with, where we try lots of ideas out on it. But when we were naming it, we were optimistic that we would eventually build the real one.
Oh, you see, I'd always misread it. I thought it was a system for verifying prototypes.
Prototypes, no, it's a prototype of a verification system. That pun is actually somewhat intentional also, but we never ended up building the real one. So this we started building, I would say, roughly the end of 1989, January of 1990 is when we started building it. And actually, because we had some prior software to build on, we actually almost always had a working version. Like from March of 1990, I can remember having the ability to do proofs and so on. And so it basically got developed over 1990, you could imagine, and then others were using it in end of 1990, beginning of 1991, and we added a number of things. We added a tactic language, lots of different tactics, and the first publication on it was in 1992. And so, both in the initial development and subsequently, we've been influenced by ideas from lots of other systems, especially SRI's prior systems. STP was Shostak's theorem prover, so that's still, Shostak's code is still in there. EHTM stands for the Extended Hierarchical Development Methodology. It was play on VDM and things like that, but that was the system that we had before. But lots of influences from the Boyle theorem prover, from VDM, Newport, Hall, Isabel, Imp, Scott, and others. Okay, and as we go, newer and newer influences are showing up. Now, one thing I want to point out is that we do have a GitHub site, so lots of other things than PVS are there as well. So you have various model checkers, SAL, hybrid SAL, SALI, SMT solvers. Actually, there's also a polylib thing. You can use it for building nonlinear arithmetic solvers, for instance. So Yikes itself has a nonlinear arithmetic solver. So probabilistic inference, evidential toolbars. Some of these are actually in development, and middleware for cyber-physical systems, something that we've done recently called that. So this is the GitHub page, and then for PVS itself, you can also go to this page, which is the a PVS homepage, pvs.csl.sri.com. So if you want the sources, you can go to the GitHub page. If you want to just download the system, you can go there and do this. Okay, so
written in Lisp.
It's written in Common Lisp, yeah, that's right. One of the truly great contributions of computer science. It's one of the most incredible programming languages there is. Okay, so let's start with a simple problem. So you have 5 candidates for an election, and the votes come in as follows: E, D, C, B, C, C, A, C, and so on. And you're told that some candidate in this does have a majority. So so that means some candidate has more than half the votes. So can you give an algorithm for determining who has the majority without actually tallying the votes for each candidate? So I don't want you to count the votes for each candidate and say who has the majority. So how would you do that?
You can see that C is the answer. Somehow.
Yeah, but it's a long list. It's, you know, millions of motives.
How many passes can we make?
One.
Oh,
One.
Uh,
5 counters.
Hmm?
5 counters.
Five?
Just have 5 counters.
5 counters? No, we don't know how many candidates there are.
It says 5.
Yeah, but you generally.
That was, you know.
So in general, you know, you can vote for yourself also. This one happens to have 5.
Traverse it into creating characters as you need them.
Okay. No, so none of the above. So it's actually very simple. You just need one counter. So you keep one candidate on one counter. So when you see E, for instance, you say, you know, E is my current candidate with a lead of 1. Okay. And then you see D, and then you say, oops, that cancels the E. So I'm going to, you know, make that. I'm going to say, you know, some candidate has a lead, has the thing, but the lead is 0. Then you see C, you make the C with lead 1. Then you see B, you cancel the C. You see C again, you make it with lead 1 again. Then at C, you see you make it the lead. You make the lead. So here you make it lead 1. Here you make it lead 2. 1 again. 2. 1. 2. 1. 2. 3. Okay. So C is, if there is a winner, it is C with lead. I mean, the lead doesn't matter as long as it's non-zero. That's the. Okay. So that's just nothing to do with the talk.
You're just trying to humiliate.
Yeah, it's very clear. Yeah. So PVS is actually, you know, quite a simple language, and you know, you know, it's easy to learn. So we have undergraduates who show up. We don't give them any instruction. They actually go off and do quite dramatic proofs. So, for instance, I have a guy now. I mean, when I call them undergraduates, they're quite extraordinary undergraduates. So we have a guy now who's doing a proof of translation from PVS to C. So he's doing the kind of mathematical nub of this argument, and so he's been, you know, doing this for maybe 10 weeks or something like that, and he's nearly done with it. So again, I didn't tell him how to use it. He figured this out by himself. And this is generally true. Most people just download it and figure things out for themselves. And I mean, it is really just as simple as I make it out to be. Theory is a list of declarations. I mean, actually, a PVS file is a list of theories. A theory is a list of declarations. Declarations can introduce types, constants, variables, or formulas. So, you know, you have various propositional connectors built in there, and you can have higher order types and so on. And you know, some pre-specified infix operators. It's not syntactically that flexible because the parsers that were there when we actually built the system. You know, we use the ergo parser, and this is the best we could do. So you know, these 2 slides are everything you need to know about PVS. So you can download it from there. The help command, I mean, this is the only thing you really need to know is how to get help. So you do meta x PVS help. And in particular, to parse a file, you can do meta XPA. To view the prelude, which is actually where you can actually learn a lot about PVS, you can do meta x view prelude file. Then if you want to type check a file, you do meta XTC, which will automatically parse things about. It'll parse the file as well. And then if you want to see what the proof obligations, you want to type check and prove the proof obligations, you do TCP. If you want to see the proof obligations, you do meta XTCCs. If you want to prove a formula, you just say meta XPR at the declaration. And you can step through an existing proof. Often, you know, when I have to understand or repair a proof, I have to step through it. You can step through it by saying Control C, Control V, Control S. You can do a read eval print loop with meta X PVS IO, and you can check the status of the theory, what's been proved or not with the SPT, status proof theory or status proof chain. That is, you can look at anything that you depend on that hasn't been proved. So you don't have to prove things in the same order. You can have, you can depend on lemmas you haven't yet proved. So it's okay to do that because lots of these things have proof obligations you may not really be interested in while you're, you want to get to the main part of the proof. And then the most important thing is how you get out of PVS, which is completely explained. So let me show you that. So here, I have PVS sitting there. You can actually declare a path for it. So I have a PVS there. So it brings up the PVS out here. Right, so that's a PVS. So I do Control X, Control C. It says, do you want to exit? I get out. Okay. So let me start that again.
The sort of goodbye world example.
So this postdoc, Cesar Munoz, this is he would always give us talks with these brackets. Start something, get out. Start something, do something, then get out. You can change the font size to 24. Is that readable?
Yeah.
Yes.
Yeah, very.
Very reasonable.
So the other thing is I'll change the context. So let's see, I have this in, don't worry about where it is. It's just a context is just a directory. So I'll change it to that. So in this directory you can have files and you can have multiple contexts and so on. There's my talk. So now we, you can see that PVS is, it starts with kind of churches, a church style higher order logic. In fact, everything about PVS is church style. That is because we see it as a written record of things. We like to see people give the types and things like that. We don't want anything being inferred or hidden from the thing. That is, everything should be written by the user and visible to the reader. Okay, so the types are going to be the primitive types, the function type, the product type, and so you can have constants, variables, applications, abstraction, pairing, projection, and then you have the record analog of this as well. So you can have record labels and record access. So there's a polymorphic equality, and there's a polymorphic.
Is that lambda really PVS syntax?
You can have lambdas if you want. You can have Unicode stuff, yeah, but it's actually you write lambda. Okay, so the simple type rules are just what you would expect. That is, a variable has type if it occurs in the context. The lambda has the function type. The application has the type of the range. The true and false are booleans. Equality is this polymorphic equality. If then else is this polymorphic thing where B and C have to have the same type, the return type of the if then else. And the pairing is going to be that product type. Actually, it's n-ary, it's not, and similarly projection.
So the type in the if condition needs to be provided, the key?
The type doesn't need to be provided now. Those things get inferred. Okay, so the advantage of using higher order logic just with this itself, just the simple types, is that things like induction can be written, fixed points can be defined. You can say that for the reals, the completeness axioms hold. That's if a set has an upper bound, it has a least upper bound in the reals. So things like that become a lot easier in higher order logic, and you can give the semantics both of higher order logic and of PVS in Zermelo set theory. So it's really in a very vanilla part of.
You somehow forbid empty sets?
Empty types?
Sets.
Empty sets. Why do I need to forbid it? It's in there. You have empty sets here. You even have empty types actually. Yeah. So the main thing when you're formalizing stuff is what definitional principles you have, because this is what makes it annoying. You want to define something and you can't define it. So typically you can have a foundational system like primitive recursive arithmetic, but who's going to write definitions in primitive recursive form? You can, but the nice thing about at least primitive recursive arithmetic is that there's a nice induction principle that goes with the recursion scheme, and this actually Goodstein is the one who invented it, and McCarthy rediscovered it and called it recursion induction. The Boehm theorem proofs are actually based on this. In PVS, we kind of take a more liberal view of definition, so we allow any kind of well-founded thing. In fact, I can show you something that So, so I wrote this last night. So this is a kind of universal recursion combinator. Okay. So this is something you can write in PVS. So you can say, for instance, take a type, take a well-founded ordering on the type, okay, on that type, take a range type, and W is your recursion combinator. So it takes a set, it takes an F with this typing. So it takes something of type T, the domain type, some, just some set Y, some function in that range, function from Y to the range. So that thing turns a set into a type, basically, and that thing. And so it says, okay, collect all the set of things that are smaller than X, the thing that you're applying the function to, okay, and then apply F to X, the set Y, and this function here. So it's just a well-founded recursion combinator. Again, this is good. Actually, this is actually all you need. You can get all the recursions out of this. Yeah.
So the major keyword is to specify the induction order, is that right?
Yeah, it tells you why it terminates. Yeah, that's right. So it expects this thing to be well-founded.
What does it mean to put parentheses around the thing?
So you've turned a set into a type. You've turned a predicate into a type. So you've turned it into the predicate subtype. So and you have predicate subtype at all levels. So you can have even numbers, odd numbers. You can have monotone functions, continuous functions, operators that compose continuous functions and give you continuous functions. So you have injective functions. All these are subtypes, and they are subset subtypes. That is, the equality relation is the same from the supertype to the subtype. So there's no.
So what if I'd written W and then X is a type T rather than set of T, and then didn't wrap my parentheses around X later on?
I mean, you get errors. You can try all that.
Yeah, let's try that.
T
And then I don't want to have X of type, at the end there. I just want X.
no, you need to give a type for X. You need some type for it.
Oh, I see. Yes. Oh, I see. Sorry. Yeah. Okay. Now I understand. Right. Okay.
So you can just give it T and see what happens.
Yeah. Well,
It doesn't parse for some reason, so I got too many parentheses. It gives you like unproved TCCs basically. So it's type, it's simple type correct, but it's not. I mean, it'll give you TCCs that don't prove. Whereas if I go back to
I
this,
suppose what I meant really is, could I write X of type, and then instead of X of type T?
no, you can actually have type things here. So at the front of the thing, you can introduce certain type things to say that I'm defining a polymorphic operation. So you can have polymorphism at the declaration level.
I see, but
So
not sort of in mind to the.
Yeah, you can't have it as an argument. So it's equivalent. I mean, so this, so we have set of T here.
Yeah. Sorry.
No, that's fine. So this, if you look at, so there are two TCCs and they prove quite easy. Okay, so that's, gotta remember where I. So this ability to introduce subtypes actually has just profound consequences. It just makes all the difference. It's a tiny tweak to the logic, okay, but it just is dramatic. It's like 99% of the advantage you get is from this simple idea of adding this. So in particular, you can define, for example, that the denominator for division should be non-zero. You can define that square root should be applied to non-negative numbers, and all the other approaches are terrible. Actually, don't use them. So this is, the kind of best way to deal with this. And the tweak is really that simple. I mean, so you have A of type this predicate subtype, X colon T with the formula B holding of it, if A with B substituted for with B with A substituted for X is valid. Okay, that turnstile there means it's valid. So what you see then is a kind of mutual dependency between type checking and this validity checking. So validity checking depends on type correctness depends on validity checking. Okay, so you see this kind of mutual dependency. And when this happens, obviously you can put in anything out there. Any formula could be turned into a proof obligation. You can't, type checking becomes undecidable. Okay, you could put the Riemann hypothesis as one of your conditions out there, and maybe you can get some solution. And so type emptiness, type equivalence, all of these things become undecidable. But they become undecidable only modulo proof obligations. Okay, so the entire system has been designed so that that's the only way things are undecidable. So I call it decidable modulo proof obligations. Okay, so that's the sense in which it's undecidable. And subtypes are just subsets. So the division, as I said, you can put non-zero real out there. So you can write a formula like this. This is a little bit of an awkwardness in that you have to have a left to right reading of it. So it's not, you can't rewrite this implies to some contrapositive form and expect it to type check. Okay, this is a definite awkwardness, but you have to live with that. It just makes the implementation a lot easier to say that under this governing condition, this must hold. And indeed, it's easy to show that the denominator is non-zero and that holds. Right? That conjecture doesn't hold. This thing doesn't hold, but it type checks. So you get this proof obligation and you can prove it. So these generate these proof obligations, and this says basically if X is not equal to Y, prove that X minus Y is not equal. And again, you find lots of mistakes this way. I mean, in fact, in 5 minutes I find like $10,000 worth of mistakes. Okay, that's how I measure the value of the mistakes that I get. So one time I just wrote this thing, this n choose k definition, and every textbook does this, but if you look at this, that's a fraction out there. So how come it's an integer? And so it says, show me that that's an integer among other things. So that is where you get caught. You can even just stare at that and say, wait a minute, why is that an integer? But if you try to prove it, you'll fail also. The other thing is that there are typing judgments that flow the subtype information. So when you apply an operator to a more refined type, you expect a more refined result out of it. So that's what these closure conditions do. So it says, for example, if you add two non-negative reals, you get a non-negative real. If you multiply two non-negative reals, you get a non-negative real. If you multiply two positive reals, you get a positive real. So the type checker does this. Once you prove this, these judgments you have to prove once, and then it flows through the system, and that way lots of things get proved because the type checker has added all this really nice type information. So for example, you can keep track of the fact that certain operators are closed under continuity and so on.
So it says special shapes as judgments needs to follow?
Yeah, this actually it's become a little more liberal. You can just put any expression out there,
Okay.
and that has some free variables in it that you give a better type, and then you say the expression has a better type. So you can say x times x as non-negative, for example.
It's like a product style research.
Yeah, so it does a kind of backward chaining on it. Actually, it does a forward chaining on it. It looks at the types of it sees if the expression finds the best, all the judgments that match the expression, and forward propagates the type of the expression. So there's dependent records as well. So finite sequences, for instance, you can say length is a nat, and then you can have a sequence that's in that length. So you can make sure it's exactly that length. And so you get a kind of very refined thing. You can keep increasing the length of the finite sequence and so on. So in the end, you get a type system in which, if you look at it both as a program and as mathematics, it can never crash. Okay, nothing can ever go wrong with it. In fact, when you execute it, nothing does, because the only thing it can go wrong is that it can run out of stack space, or you can run out of heap space. Those are the only two ways you can go wrong. All the other kinds of errors are gone. No uncaught exceptions, no out of bounds array accesses, no nullity references, and so on. And you can do all kinds of tricks with it. You can put the specification of the function, into the type. So you can define G91 and say that F91 actually is equal to the G91, and then this helps you actually prove the termination of that. So if you can assume this type of the recursive call, then it makes it possible to prove the termination of that function. And so you have theories. So you can have theories like this. Again, this is higher order. So you can have T is of type. You have the ordering relation. You have the meet out there, and you can say that I'm assuming on those things. You can actually put it into the predicate subtype, so you can put it here. You can say I'm assuming that it's reflexive antisymmetric transfer. The greatest lower bound is a lower bound, and it is the greatest such lower bound, and so on. And then you can define the least fixed point and show that the least fixed point is a fixed point. And I think again the advantage of higher order. And furthermore, that thing that was a complete meet semi-lattice. So you can actually turn that into, you can say a complete meet semi-lattice is a complete lattice by just importing it with everything flipped around. That turns it into a. And then you have people call it inductive recursive data types, whatever, the things like lists and trees and so on. And you can have these kind of mutually recursive versions of these, similar to what Jeremy showed yesterday. So you can have a tree that has lists of things. You can have a tree that has a sequence of things and so on. You can define ordinals, all of this with this. So there's a bunch of things that people have done. So this is only a very partial list. I've taken some things out of this NASA lib. So these are various proofs that people have done. Actually, don't know what many of them. I mean, these I don't know what they are, but it goes on quite a ways. So there's lots of trigonometry, graph theory, analysis, and actually several books have gone through the system as well. So there's I think a data refinement or something book by Willem Paul de Roever. There's a hardware proof by Willem Paul. Then a couple of books. There's one that just came out. I think maybe Mauricio, someone has written a book that uses PVS in it. Doron Pellet has a textbook also that uses PVS in it. So this is actually the Sturm and Tarski's theorems are the ones that Marie-Françoise mentioned the other day. So this is they've turned it into a decision procedure for the reals. So you can get a decision procedure for the reals that's been verified. Okay, so let's start with the tutorial part of it. So at this point I'll switch to so the Booleans, as I said, are just a kind of built-in thing. So we can look at that's a theory out there which has some simple Boolean examples. And actually we could learn all about PVS just from Booleans. It's not that much more to it that you need to know beyond the Booleans. So as I told you, you can pause this. You can say net x PA, I think. So here it's actually restoring from the binary. So it's just saying I just got it. So if I say type check, it says it's already type checked. So you might say, look, I don't care. I want to type check from scratch. I'm doing a demo. I want to really do it. So you can hit the keys really hard. So the way you do that is you say Control U, meta x, DC. So that redoes the thing. It ignores what it has in the binary form. Redoes it. And no TCCs were generated. And as I said, you can actually then do a proof. So you can do I step through the proof, for instance, and it has a proof in there already. And since this one just comes from applying the kind of disjunctive rules of the propositional sequent calculus, so the right implies the right disjunction and so on. These are all disjunctive strength rules. So if you say flatten, so if I type flatten out here, so that finishes the proof, okay? Because it turns that into an axiom. So let's try the next one. So ignore what's in there. So again, you might think, okay, the implies obvious thing to do is flatten. So that gives you this sub-goal. So it says, so this you can see is a sequent arrow. Okay, those are the antecedent formulas, these are the consequent formulas. There could be many consequent formulas, it's classical logic. Okay. So but here, it did not do anything with the left implies because that's a conjunctive strength. Okay. Right? So there's a command called split, which does the things of conjunctive. And that finishes the proof. Okay. Good. Yeah. So here's another one.
As a person playing around with this, how would I find out that there was something called split?
Yeah, I told you already, MetaX help PVS or PVS help or whatever. You need a combination of those. So PVS help prover commands or something like that. You'll find out. And actually, there are some tab bindings also. I think if I say tab F, it flattens it. If I say tab S, it splits it, and then just return for all, things like that. So you can then say, I can say tab S again. So this one I need to flatten, so I say tab F. So I can save the proof if I want. I can save multiple proofs if I want, and so on. So here's, so this is not hugely interesting because it's rare that you're actually proving something that is valid. So at least for me, 95% of the time, I'm beating my head against something that is not a theorem, and I need to find out why it's not a theorem. And so here is this thing where I have conjecture, so something must be missing in it. So let's see what happens out there. So if I say tab flatten, okay, I get this. So then I have to say tab S, and it just kind of applies it randomly. I can do a tab S again. So that gives me a sub goal out there, and it says basically prove A implies B, and that's where it fails. So this is the kind of thing that went wrong. So this is what happens basically in all these proofs. So most of the time I want to get quickly down to something that looks like this and say, oops, that's the problem. I think I know how to fix that. And then I basically fix the formula. Mostly I can read, I can retain most of the proof that I've done, and I rerun it again. Find the next bug in the proof and go on.
Is it able to detect that this is impossible?
So yeah. I know as a meta theorem that if you reach this, it's impossible. But let me show you a couple of things that go in that direction. So let me undo. You can, by the way, undoing is the bulk of what I spend my time doing. Okay, so undo. So if I say undo 100, it goes back to the original goal. Okay, so I'm back where I started. So one of the things I can do is that I can hit it with something called Prop, which is a strategy that's built on top of flatten and split. It just iteratively applies flatten and split. So do that, and it comes up with two sub goals. So this is one, and then I think tab shift P with the postponer. I can look at the other sub goal that's also an A implies B. In fact, it ends up with two copies of B there. So essentially, I can just circle around this and come back. So you're just kind of circling through the sub goals. Okay, so you're looking at that, and so if prop doesn't get it, it's not propositionally satisfied. Okay, so that's the propositionally valid. So another thing you can do, in addition to prop, is that you can call something called BDD simp. So this basically just calls a built-in reduced ordered binary decision diagram routine. Okay. And this is quite interesting because instead of two sub-goals, it just gave me one. And that's because it minimized the Boolean form. Okay, so it was just able to give you one. Now that, again, if BDD simp didn't get it, clearly this is a counterexample. Okay, proposition is a counterexample. So again, I undo that. And then I can call an SMT solver as well. And an SMT solver does start solving along the way, so you can do that. So you can call yikes. So this is again, this is yikes 1. So this is Leo Demura actually built yikes 1. So it gives you this truth assignment. It says there's a counterexample where A is true and B is false. And it does that with even things like arithmetic constraints and all that. It's quite helpful to find those counterexamples because that's something you want to know. Typically I have these problems getting things that are one off. Is it k plus 1 or k minus 1? You get that wrong, and so the proof fails, and you can get the thing saying, this is why it failed for this particular instance. You can also do yikes 2. So that also does it, but I haven't yet defined the thing that does the translation back. So I haven't got the truth assignment back yet, but you can do yikes 2 as well. And yikes 2 is way more powerful actually. I think yikes 2 is probably the most powerful of the SMT solvers there on many of the categories. Okay, so that's that. So proving norm theorems, and then you can do Pierce as well. So again, you can just do it with all of these things. So that's example 1. So then we can look at, what else do I have? Quantifiers. Okay, so here's some things involving quantifiers. So let's see, this says, so one thing to keep in mind is that these types can be empty. Unlike conventional textbook logic, the types here could be potentially empty. So something like that, for all x that exists of y, okay, is that valid or not in the presence of empty types?
Yeah.
Why? No, it is valid actually.
Is the universal quantifier.
Yeah, because the universe quantifier of the empty type is okay, it's valid. Anything is valid for universal. And if it's not empty, well, there is one. Right? Let's see what I do. Okay, so there are various things you can do here. So column bang actually generates a name for it. Okay, it generates this expand 1. And then, I don't know what this is, but
What's the key shortcut to get to the screen again? What do you click to get from there to the proving?
Control C, Control PS.
Okay. C, Control BS.
Control C, Control PS.
E.
No, the S has no control actually. I think I
Okay.
got that. I had a typo on my slide.
I did it.
Yeah. Okay. But you can also, there's a thing you can do called skip that someone's defined that just replaces the variable x with the constant x. So it retains the name, so it doesn't look ugly. And then you can actually say inst plus x, and that finishes the proof.
What does C plus refer to?
What the plus is below the line, minus is above the line. So plus is consequent formulas, minus is, and you can actually number the formulas if you want. It starts to kind of make proofs kind of non-robust if you get too specific about it. So that's why we have the pluses, minuses. Those tend to stay fairly stable.
Can you assign names to your?
You can assign labels and use the labels actually, and you can build those into your strategy so that you can say that's the induction hypothesis, that's the induction conclusion. People do that actually. They design their own proof system, and actually they do all kinds of weird stuff. They one of the early things we did is actually embedding something, a model interval model logic called duration calculus. So you get the modalities, and you can actually, it's a shallow embedding. You're using the PVS expression language, but to the user it looks just like their surface syntax. And so these are kind of of some of the benefits of using hierarchical logic. So yeah, I mean, you've already seen quantifiers, so you can do other examples. And there's things like the drinker's problem, and there is always one person such that if that person drinks, then everybody drinks. Okay. So that's a theorem, as it turns out. So you can do things like that. Okay, so let me just go to my slides and see where I am. And all that. So I only made up all these slides to kind of put out there because it's like a reference manual. You can use it if you want. Equalities, okay, so let me see if I have something to do with that. Okay, so here are some equality theorems. So let's look at this one. So there are many ways again to prove this. So if I just say, so tab 1 is I'm stepping through the proof. So I'm just saying flatten, I'm following the proof that's out there. So that turns it into this antecedent formula. And then I can actually, try a replace, for instance. So I can do okay. So that actually doesn't finish the proof. So it just makes the formula bigger and bigger. Okay, but if I go back and I say replace -1 dirt RL, okay, and that actually has a better effect. And now I can actually say assert, for instance.
So when you write assert, which database is used for simplification? Is there some?
Yeah. So
I guess.
Each sequence that you're staring at, each goal sequence or whatever, has a context which the decision procedure uses. So it's everything that's been asserted before. And what's going on with assert is actually very complex, but I'll break it down for you. At the first level, it's asserting every formula in the antecedent positively, every formula in the consequent negatively. So it's asserting that. And then if that gives you a contradiction, you're done. But it may not, and that's okay. Then you're actually simplifying expressions relative to that context. So when you go inside a quantifier, for instance, for all x something p of x, you're simplifying p of x knowing the type for x. Okay, that information is there in that context. If you're doing an if then else, for instance, you're simplifying the then part knowing that the condition is true, you're simplifying the else part knowing that the condition is false. In the simplifier, you're also rewriting. Your assert also has a context of rewrite rules. And some of the formulas you can also actually take the antecedent formula and put it in as a rewrite rule if you want. But you can bring in lemmas and so on as rewrite rules. When it does the rewrite rules, it's going to use the context again, because matching might give you proof obligations. You might say this only applies to, for example, non-negative reals. Okay, matching might give you proof obligations. So it uses the context to discharge those. But it also uses it to simplify the right-hand side. It recursively, simplifies the right-hand side, because you don't, you say you expand a definition. You're only interested in the case of the definition that's relevant to the left-hand side. So you do that. So there's just a lot going on contextually in that assert. And the other thing you can do is you can actually do things like grind as well. So there are lots of variations on grind. So everything is, when you're looking at a sequence, you're trying to smash it, bash it. These are the kinds of commands you have. You tend to have a very physical kind of view of how you do the proof.
And is there just some heuristic for instantiation?
Yeah, there is a heuristic for instantiation. It's not good at all, but it is there. So it's question mark. Does it grind actually uses a heuristic for instantiation? There's a polarity flag you can give it that's a little better because it only matches when the polarities are right. So it gets lots of things. It gets like 8 out of 10 things. On the remaining 2, it'll be just annoying. Why did you get 0 for that? Okay? Where the hell did you get 0 from for this instantiation? It just makes you mad. The problem with this is that if you kind of get too fancy about it, you start doing a lot of search. So here, grind doesn't do any search. It just slaps down whatever it is. So let me show you some examples of this. So the first one, let me do this big num example. Strange one. So this is big number arithmetic. So here, big num out there is a theory, but the base is going to be above 1. So I want the base to be not 1. I want it to be 2, 3, 4, and so on. So that's the type. It's saying base should be at least 2. Okay. Then it's saying that the carry in out here should be 0 or 1. Okay. It's up to 1. So it's 0 or 1. So that should be a carry in. And that's what you expect the carry in to be. A digit is going to be below the base. So it's going to be 0 to base minus 1. Okay. And then you say this judgment out here that 1 is always a digit. Okay. That's correct. Okay. So then you give yourself ijk of type digit, and then a big number is going to be a list of digits. You've already seen lists. Okay, so you give yourself some variables over big num. And here, what you're going to do is you're going to define what it means to take the value of a big num as a natural number. Okay, so it says if the big num x is empty, then its value is 0. If it's got some kind of least significant digit I, then it's I plus base times the value of y taken recursively. Okay, so the I is the least significant digit, so it's written in little endian form. Then this thing is a digit addition, so it's going to be adding one digit to a big num. And the way it does it is it again case analyzes x and says that if x is empty, okay, then if I is equal to 0, return the empty list. Don't return singleton 0. Okay, that's a redundant representation for 0. So you don't want that. You want it to be. Otherwise, just return the singleton I. Okay, that's it. There's nothing in x anyway. If you have a least significant digit j in x, then if I plus j is less than the base, then you make that the least significant digit, and then just return y out there. If it's greater than or equal to the base, then you subtract the base and recursively call digit addition with y and 1. Okay, so it's like a carry out now. Okay, that's the. So you can prove, the correctness of x plus I is equal to the value of x plus I. This plus is the plus operator there. That plus is just arithmetic plus. And by the way, one of the significant points is that all the arithmetic types are subsets of each other. Okay, the natural numbers are a subset of the integers, are a subset of the rationals, are a subset of the reals, and so on. So and plus is the same plus for all of that. Now, the next thing here is a little strange. So big plus is going to add x plus y with a carry in right there. And remember, the carry in can be 0 or 1. And if x is empty, it's just y plus carry in with the previous plus. If x has the least significant digit j, then you case analyze y. And if y is empty, then it's just x plus carry in, just like this symmetric case to that one there. And otherwise, if you have a least significant digit k, then what you do is you add the carry in, these two least significant digits. If it's less than the base, okay, then here I make a mistake. Okay, I flip the cases, which is very common with me. So instead of out here, if sorry, it's so this doesn't have a mistake in it. So let me put in a mistake. Okay, so what I'll do is if it's less than the base, I'll subtract it. I flip the cases. Now what I'm going to do is I'm going to type check it. I went through, and I'm going to say let's try and prove this. Okay, there's a strategy called induct and simplify. I hit that with that. That proves the correctness of the digit addition. Then I ask it to prove this. So again, I use the correctness of the digit addition as a rewrite rule, and it proves it. Okay. I screwed that definition up, and it still proved it. And the reason for that is that I screwed it up in a very consistent way. I made two mistakes to correct that. So here, because it's less than the base, I subtracted the base, but I did actually have a carry of 1 out there. So, you know, I was consistent about it. I conserved the value. So that's why I proved it. Here I did not subtract it, I kept the carry as 0. And you know, what you can see is that when I actually try to prove the TCCs, so what happens is that it ends up with 2 unproved TCCs out there. Okay? So, and if you look at the TCCs, you'll see what those are. So if you look at this unfinished, so this one complains that you know, I can't show that this thing minus base is greater than or equal to 0. Indeed, you shouldn't be able to do that. Okay, right? And the next one. Next one shows that it says that I can't prove this is less than the base. Okay, if it's not less than the base here, why is it less than the base here? Okay, so those two fail, and that's what you have. And interestingly enough, you can actually you know, take this incorrect definition and evaluate it. So you can see what goes wrong. And so I take this. And that's the answer I expect. Okay, that's the correct answer. So that's what I get. This is base 10, remember. So I get, you know, each of those digits is not a real digit. It's messed up. Same thing I can do with this other one. It's got negative digits of it. Okay. So but if I go back, I exit. Okay, so everything is fine. And I come back here, I do the again. So let's see if we get the answer that shows up on the right hand side. Yeah. That's 779. So, by the way, that Lisp evaluator that's there, it's got a thing where it does a destructive update optimization. So it actually, you know, even if you give it applicative code, it works, you know, works with it so that when it's sorting an array, it's sorting it in place. It's not actually making copies and so on. So it is actually quite fast. And people use it to actually generate, like for example, decision procedures and model checkers and things like that out of the system. And actually, more recently, I've defined a PVS to C translator. So it basically takes the functional subset of PVS and translates it into imperative C. And it uses reference counting both to do memory management as well as to find out possibilities for destructive updates. So when it sees that an array is just singly referenced and no longer live in the program, it actually updates it in place. And so here, I'll just show you a couple of examples. This one is actually just showing you that you know, you can have various arithmetic things, 8, 16, 32-bit, and so on. So here, actually here I'll show you just the Lisp interface and DC arithtops. So that's forcing the type check. Then actually all the TCCs are approved. I can do that, but it will take too long. Then I do PVS to C theory of arithtops. So it generates code in an intermediate language, then it does a little bit of kind of static analysis in intermediate language, and then pretty prints C code from that. And you can actually see the C code. I mean, you can see it actually out here. So you can see that it's generating that stuff. And so if you, there is an Emacs command for doing this, I'm not sure why. So it generated a fresh one. So I go there. As part of this, I print out a little cheat string. And say this, I need to add a main that I've hand defined. It generates these answers. Total CPU time is shown up there. Let me show you one other example. So this is a small matrix transposition thing.
So the underline 0 is the, so underscore 0 is the first component or the major bits? So when you're running the compile C program,
Yeah.
the output saying something underscore 0.
What is the thing?
Do you remind me again?
Oh, these are just labeled names. They're just names I'm using to print.
Oh,
This is just stuff in my main. It's not in the.
okay.
So small transpose. So so as I said, it's a metric transpose thing. So again, I go there. I say DC small transpose. Pick up my little cheat sheet. And add the main to it. So here it has 0 on the left and 2 on the right. That's the input I'm giving it. And I expect to see 0 on top and 2 at the bottom. So that's what you got. So the 0 on top, I'm just printing out a few of the things. Right, so and essentially it works at C-like speeds. So if you try to write that C, A, you would never succeed, and B, it would be roughly at the same speed. And it's actually trivial to do this. I have no idea why people did not do this in, say, 1960. Okay, it's actually a homework exercise to go from a functional language to C. And as I said, this undergraduate is doing this proof, and he's been making really good progress with it. So he spent about 10 weeks on it. More or less done in a couple of weeks. So that's the summary of, that's basically a short overview of PVS. And,
What does PVS do about sort of axiom of choice or Hilbert?
it has a built-in Hilbert epsilon.
But you have empty types.
Yeah, it checks that. It checks. I mean, you can say, the type has to be
Oh, I
non-empty or so on. You can actually make that out.
Right.
A condition of the type.
Yeah.
So if you just say type plus, that type has to be non-empty. Because actually, even just declaring a constant of a type, it generates a proof obligation saying, show me that type is non-empty.
Good.
I mean, it's mainly for finding mistakes. I mean, when we actually reach QED, it's complete anticlimax.
So I noticed your natural numbers were a subset of the integer subset of rationals, etc. How do you construct those numbers on top of each other, or do you just axiotize the biggest one?
Yeah. So if you actually did it in a definitional way, then naturally you wouldn't get that subset relationship. You would only get like an embedding.
Right.
But here we just axiomatize the reals and then
So if you wanted to, do you have the complex?
Yeah, if you wanted, you could add the complex numbers in there into the
I mean,
hierarchy.
if you wanted to add a bigger set of numbers
You could,
and then
yeah.
make the
Yeah, so there's a,
Numbers,
there's a,
subsets, how
yeah,
would you
there's
do
a
that?
number field on top, so you could actually bring in things in between those as well.
So how do you identify the construction? I mean, the subset of the new, you've got some sort of quotient stuff,
Right.
which is your closure of something.
Mhm.
And then the thing you started with, say the complex numbers, you're building quaternions or something.
Yeah.
How do you identify the quotient with the thing you already have?
So you'll basically say it's a subset of those. So you'll define the reals as a subset of those.
So you'll do the construction carefully so that
Right.
it is a subset.
It's a subset, yeah. Anything else? And we should basically move on, sir.
Thank you very much.
Thank you.
And I have like
So 5-minute break. if everyone.
pause this.
Okay.